In these notes, we are going to do the introduction of exponential functions, but before we do that, want to review the exponent properties that we know, which is the zero exponent property. Anything raised to the zero power is a 1. If a negative is outside the parenthesis, though, or if there are no parentheses in the number and the base is negative, then it would actually be a negative 1. And then our second property, negative exponents. We are not allowed to have negative exponents, so we are going to circle the base that has the negative exponent, and we're going to move it to the location that's kind of opposite of where it's at now. So if it has a negative exponent in the numerator, we're going to move that base down to the denominator and make the exponent positive, or vice versa. If the base that has a negative exponent is in the denominator, then we're going to move it to the numerator and make that exponent positive. So for example, number 1, we have 4x raised to the negative 2 divided by y to the third. The only base that has the exponent that's negative is the x. That 4 has a positive 1 as an exponent, even though we don't write it. So the cool thing about this is that the 4 divided by y to the third stays. However, we have to write x squared on the bottom because it was in the numerator. Now we're going to move it to the denominator. Please write it in alphabetical order. That's why I put x squared before the y to the third. Now for number 2, we have 5 to the 0, a to the third, b squared, all divided by c to the negative 4. 5 to the 0, we already said was 1, anything to the 1 power. Since we have this a to the third and b squared next to it, we don't have to write that 1. Because if we have 1 apple, we just say, oh, we have an apple. We don't have to put that 1. Now the second thing that we have to look at is this negative exponent. The base that has the negative exponent is c. So we're going to move it to the numerator. Now, like I said, technically it's a 1, a to the third, b squared, none of that moves. The only thing that moves is c to the fourth. However, that 1 is not needed, so your final answer would be a cubed times b squared times c to the fourth. Now the third problem, we have 7 divided by z to the negative 8. Only thing that has a negative exponent is z. We're going to move it up to the numerator. 7 stays place, so then we have 7z to the 8. Now if you look at number 4, that negative sign is inside the parentheses, so that is actually still just a positive 1. We're going to move b raised to the negative 2 to the denominator. Since 1 is the only term up top, we have to keep it, so we can make this a fraction. So number 4 would be 1 divided by b squared. Now, in the introduction of exponential functions, students will be able to determine the characteristics of an exponential function by exploring the graph using the sliders in the guided notes. Students will be able to identify the initial value, that should say constant ratio, and create an exponential equation in the format y equals a times b raised to the x. So exponential functions, and you don't really have to write anything in here. Exponential has this format. If you notice, the x is in the exponent. A is going to be your y-intercept for this class. It's called the initial value. It's where you're going to start. So if I move this up 2.6, that's why it intersects the y-intercept at 2.6. But the b can't be 1 because that's a horizontal line. If we make B 1.3, notice how it's increasing. It's going up quicker and quicker, so on and so forth. Now, if we make it less than 1, look how cool this is. Now, we are going to stay kind of like in the decimal between 0 and 1. This is actually called a decay because it's slowly decreasing. While it's decreasing, and it's going all the way down. And then we're also going to talk about key features such as asymptotes. Notice that my graph looks like it's going to touch the x-axis. You're actually not. It's going to approach 0, but never actually reach 0, which we'll talk about later. So this exponent that is our variable x makes the graph look the way it does. Now let's dive deeper into more about the exponential function. So notice Mario. Mario is starting off the screen, going pretty slow and then going really fast. So in this part, I just wanted you to write, what did you notice? What do you wonder? Why does he start off so slow but then goes really quickly? Anything that you think of, you can put here. Now it says the function to the right gets closer and closer to the x-axis, but never quite reaches it. When a function approaches a line in this manner, the line is called the asymptote. So graphed to the right is g of x, we could say y equals 2 raised to the x. So it says, remember a horizontal line is y equals. So if I put y equals, let's say -2, this would not be the asymptote because we're trying to figure out where does this line kind of sit on or try to sit on, because it's never technically going to reach it. It's approaching it. Let's try -1. Nope, not quite. Let's keep going up. Now, if you notice, the graph is trying to sit on this asymptote. So y equals 0 is the asymptote of y equals 2 raised to the x power, because that is the line that the graph is trying to sit on. All right, another important feature or characteristic is domain and range. So we've talked about this before. Domain is the x values, and of course the range is the y values. Now we have several different ways of writing. I'm going to show you interval notation. Now parentheses is when it's kind of like an open dot. It's a boundary but not included. So whenever we deal with negative infinity, it has to be parenthesis because negative infinity is just something that the graph approaches. Positive infinity is also something that approaches. Let's say our graph doesn't touch 5 but approaches 5 and then goes to 6. So it can have a very different feel. Interval notation is not an ordered pair. It's just telling you what numbers the graph goes to. Now remember, domain is left and right. The range is down and up. So this part would be included because it's a bracket. This would not be included because it is a parenthesis. Now you can have so many different combinations. It just depends on the graph. But remember, not an ordered pair. So please never think that. Now, it says in this graph, click on the orange dot and move it to the left and right to cover the domain. So this, once again, is y equals 2 raised to the x power. So if you cover this, how far left can you go for the graph to stay covered? Does it stop at a point? Does it keep going on? If it keeps going on, where does it go to? So even if we zoom out and zoom out and zoom out, this shaded will always go to the left. If it always goes to the left, we call that negative infinity. Now, this graph will always go to the right. I understand that it doesn't look like it's going to go to 50 or look like it's going to go to 100, but I promise you, if you wait long enough, it's going to go all the way to the right. All the way to the right is called positive infinity. Now, how we use interval notation, we have to decide, are we using parentheses or are we using the brackets? We are going to use the parentheses here because we're dealing with infinities. Whether it's positive or negative infinity, you use the parentheses. So on the next slide, that's where you're going to put your answer. So you have to use the parentheses, minus, and then spell out infinity. I gave it to you, and it changes it for you. And you're going to check. Good work. Now we're going to do the same thing for the range. The range is how far down does the graph go? How far up does the graph go? So we have to think about the asymptote that we did in the previous slide. Where is this trying to sit? If I keep, kind of like zooming, that graph is trying to sit at x equals 0. It goes all the way there, but how about this? I'm sorry, y equals 0. Y equals 0 because it's the range, right? How far up does our graph go? Does it ever stop going up? That's the question that you need to ask yourself. Since you can zoom out as much as you want, no matter what, that slider is always going to go up. The range is always going to cover this graph. So we know that this graph is trying to sit on 0, and we know that it's going all the way up to a positive infinity. Once again, once we have the lowest part and the highest part, we have to determine, do we use parentheses or do we use brackets? Now, we only use bracket if it's included. 0 is not included because it's trying to sit. It's trying to approach 0. It's going to get smaller and smaller, but it's never going to reach 0. So that's why we use the parentheses. And then the same with the infinity. Whenever you have an infinity, whether it's positive or negative, you're going to use the parentheses. So let's enter that on the next slide. All right, it works. And then you're going to try it on your own. So for your turn, we're going to talk about exponential decay when a graph goes from left to right, but it's decreasing. So if you look at Donkey Kong started really fast and then he slowed down near the edge. Now remember, the equation of the asymptote is, where is this line trying to sit? It is trying to sit at y equals 0. It's going to try to get to 0 on the y values, but never will reach it. So just a friendly reminder, most of the graphs in our class will always be y equals 0 for the asymptote. For the domain and range, so remember this is a decay function. How far left can our red graph go? How far right can our red graph go? I can move this slider forever and ever, and it still touched the red line. So we call that negative infinity. How far right can my graph go? It can go to positive infinity. Now, since infinity is kind of more like a boundary, we're going to use the parentheses. So in slide 14, the domain of this function is going to be negative infinity to positive infinity, because every single x value would work for this function. Now the range is a little more difficult, right? You have to look at this. Yeah, of course the slider can go all the way down, but where is this trying to sit? What y value is this graph trying to sit on? And that is our 0. How far up is our graph trying to reach? I could move this slider forever and my line would still be touching it. So the bottom number is the number the graph is trying to sit on, which is 0. Our top value is a positive infinity because our exponential graph is trying to reach on forever. It's trying to go to positive infinity. Even if I zoom out and I move the slider up, it's going to keep covering the y values of my graph. We're going to use parentheses because our graph is never going to touch 0. So 0, comma, and then it's reaching all the way up to positive infinity. So that's for our domain and range. Once again, our range for this class will always be trying to sit on 0 for exponential functions, and always trying to reach positive infinity. Now, something that's important for exponential functions, an exponential function is a product of initial amount, which is really the y-intercept, and a constant ratio, which is the pattern for the table. So I do want to mention that this is going to be the y-intercept in our class, and this is going to be the multiply pattern. So we're going to do that. You can use the time symbol or you could use the parentheses. Either or works. So let's move to the next slide to kind of visualize what this equation is going to look like. It says, what do you notice and can you describe the pattern? So let's play it again. So first we start with one red block, go to 3 blue. Then if you can count quickly, that's 9 green, and then all the way to 27 purple. So a lot of you guys in class said it's increasing, it's going really quickly, it's getting tall very quickly. Some of you even said multiplying by 3. And let's dive more into that. So remember, this is all patterns, okay? So we are at, let's call this X, let's call this Y. So this is the stage, what stage number we're at. So stage 0, 1, 2, 3. And then our Y is how many blocks. So we're starting out with 1 block. Then we're moving to 3 blocks in stage 1, 9 blocks, and then all the way to that purple tower, you're going to have 27. So we're going to use that information in the next slide. So I'm going to move to slide 19, and I'm going to put that information in. All right, so number of blocks is 9, number of blocks is 27, and if we even continued more, we're going to get 81 blocks. So we have to think, how many blocks did we start with? We started with 1, and that shows up on the y-intercept. That shows up when x equals 0. So the initial value is 1 because that's our starting point, our y-intercept. The constant ratio is a bit harder to find. Remember, constant ratio is talking about the pattern. How am I going to multiply from 1 to 3, 3 to 9, 9 to 27, 27 to 81? And that number is multiplying by 3. Now, I highly recommend, if you can't see it right away, especially when we get into fractions, I'm going to show you a trick. So the pattern is 3. So the constant ratio is 3. So here's the trick. If you have a y value, let's say 81, divide it by the next y value, which was 27, and that's going to get you 3. So if you work backwards, you're going to realize that the constant ratio is 3. You can do this for any one. You can do 27, divide by the next y value, and you're going to get 3. 9 divided by 3, you're going to get 3. Now, what does all of this mean? That b value, that constant ratio, is really important when we're making this equation. So we have y equals 1 times 3 raised to the x. The reason why we have that, our initial value is 1. That's where we got this from. That's our a value, so I'm going to put it into my a. We said the value or the pattern was 3. So then I'm going to put it in my b value. Now you can use parentheses, you can use the multiplication symbol. It's totally fine, whatever one you do. And make sure you put an x in the exponent, and then just confirm that you got the right equation. Now, it says, what is the initial value? Remember, initial value is the y-intercept. So, initial value is 128. Is 0, 128. So we're just using the y value. Now we want to come up with a pattern. To get the pattern, start with 64, divide by 128. Now this is going to get you a fraction, and that's okay. 64 divided by 128 is a half. So this is going to be your constant ratio. So let's think about this. I said its a constant ratio is a half. Let's put it as a fraction because that's what you multiply to get to the next number. And when I say next number, that is our y value. So if I multiply by 0.5, I'm going to get 64. Now you can even put this in the table. 64 times 0.5 gets you the 32. What's 32 times 0.5? Gets you the 16. Notice that it's decaying. 16 times 0.5 is going to get you 8. Now let's put it all together. Our A value is our starting point. So this is our A value. That's our B value. So our A value we said was 128. We said our B value was 1/2. If you want to write it as a decimal, that's fine. It's going to get you the same answer. So y equals 128 raised to the x power. Goes through everything. We know we did it correctly. So once again, if you want to write 0.5, it should work. And it does. Okay, so it does not matter if you write it as a decimal or as a fraction. So then this should be multiplied by 0.5. And then you can do the same thing for slide 24. I'm sorry, slide 21. So our initial value is 0, 3. Is that our y-intercept? So our A value is 3 because that's the y value. Now for the constant ratio, we have 3 and we have 12. So I'm going to do 12 divided by 3. And I'm going to get 4. Let's confirm. Does 3 times 4 get us 12? Yes. So we know our constant ratio is going to be 4. Okay, so we know that constant ratio letter is B. So we can say B is 4. Now in the table, once again, you can actually just do this. 12 times 4 gets you 48. It graphs it. Do the next number. 48 times 4 is a very big number, 192. 192 times 4 gets you a very big number. So let's put it together. We have this equation. We have y equals A parentheses B raised to the x power. So we said our initial value, our y-intercept is 3. Our b value, what we're multiplying by, is 4 raised to the x. It goes through our points. Get a smiley face, we know that it's correct. And then the last one, our initial value is 0, 80. So our A equals 80. That's a y-intercept. Constant ratio, do yourself a favor. Do the bottom y value divided by the top y value, the one that's right next to it. you're going to get 1 over 4. If you want to keep it as a decimal, that's fine, or 0.25. So let's verify. If I put this into the calculator, 80 times 0.25, I'm going to get 20. Now use the table to get you the next one. 20 times 0.25 gets me 5. 5 times 0.25 gets me 1.25. 1.25 times 0.25 is going to get me even a bigger, I guess I should say a smaller number, 0.3125. So we're going to put those items together. Our A value is our initial value, which is 80, so y equals 80. You can keep it as a fraction or a decimal, doesn't matter. Close parentheses, raised to the x power. So all we're doing is finding the constant ratio and locating the initial value and making an equation out of it. So we will definitely have more practice as the days go on. Please email me if you have any specific questions. So the goal for these notes are for you just to finish, and then for sure in the next following days, we're going to practice more and more so you guys can truly understand what's going on. All right, I hope you guys have a great rest of the day.